Right, so welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're very lucky to be joined by Marusa Bradac, who's come across to us from UC Davis, where she's an assistant professor. She did her PhD at the University of Bonn in Germany, and then did a postdoc at the Kavli Institute for Particle Astrophysics and Cosmology at Stanford. And then she was a Hubble Fellow at UC Santa Barbara before taking up her current position at UC Davis. Her career interests revolve around observational cosmology, dark matter, and observations of the first galaxies and galaxy clusters using gravitational lensing. She's interested in studying dark matter and its properties over a wide range of scales and environments to discriminate between different models for dark matter. In this way, she's been interested in looking at the bullet galaxy cluster and other merging galaxy clusters, as I'm sure we're going to hear about in today's talk. And she's also interested in using strong and weak lensing to detect dark matter and observe the early universe as well using that same technique. So please join me in welcoming Marusa.
Thank you very much, everybody. Thank you very much for coming here, and thank you very much for a kind invitation to this institute. Since I first heard about it, I was always very jealous about it because, you know, how cool is it when you can say that you're studying extraterrestrials to your kids? But so I'm not studying extraterrestrials, but I am studying dark matter, and I am studying first galaxies. And today I'm going to be presenting you things from my research on those two subject matters. So, but before I dwell into the dark side of the universe, I'm here presenting the light side of the universe. Can anybody recognize this constellation? It's Orion, indeed. So it's a view of the night sky from our Earth. Clearly not from here, because you can actually see the Milky Way. But if you go to a darker spot, you might be able to see something like that on the sky. So what I'm going to show you is a movie in which every single star, every single galaxy that you will see are at their correct measured position and correct brightness. In addition, you will see images of nebulae, and those are images from Hubble Space Telescope. The only thing Brent Tully did with it is they're enlarged by a factor of about 10, just so you can see them better. But this is actual astronomical data. So this movie, it's not Hollywood, but it's actually real scientific research. So when we are flying from the Earth, you very quickly see that Orion is just superposition of stars. It's a chance alignment rather than actually stars being connected to each other. And so here we are flying past the Orion Nebula and the Horsehead Nebula, and you can see these are the places where the new stars are born. So these are the images of some of the nebulae that we see. As we are flying further, you can now start to see that that band that we call the Milky Way on the sky is actually starting to look a little bit like a disk galaxy. So you can see the disk emerging, okay? So our galaxy is a spiral galaxy. We are flying here at immense speeds, okay? So we are doing about 50,000 light years per second, which is a lot. But you can now see our very own Milky Way, and our very own Milky Way is a spiral galaxy, as you might have known before, and you can see these beautiful spiral arms from our own Milky Way. But it turns out our own Milky Way is just one of the many, okay? So here are the Magellanic Clouds. For people in the south, they have seen them before. We are now flying further, leaving our own Milky Way, and getting to the to the next big galaxy to ours, which is, anybody? Andromeda. Very good. I don't need to give this talk, right? It's an Andromeda galaxy, and you see it's just another spiral galaxy like ours, slightly bigger. It's going to collide with our galaxy most likely. But today what we are really going to talk about is not individual galaxies, but they are actually places in the sky where thousands of galaxies are bound together. They're bound by gravity, and these kind of structures we call galaxy clusters. And you will see as we get closer to this particular galaxy cluster, this is a Virgo cluster, is the closest galaxy cluster to our own Milky Way, that if you have a very, very trained eye, you might recognize that there are going to be fewer spiral galaxies in that cluster. But what's important, and the only thing you really have to remember for this talk, is that these these galaxy clusters are about 1,000 galaxies together. In addition, each of these images has been magnified by a factor of 10, remember? So you need to think about it shrank together. So there is a lot of space in between the galaxies in galaxy clusters. At the end, you have seen the big galaxy, which is in the center with a huge jet coming out. Usually those galaxies have a supermassive black hole in the center. But this is not the subject of our talk today. So the subject of our talk today is about the dark side of the universe and about dark matter. So if I get to it, in the second part of the talk, I'll also present something about the first galaxies, and you will see how the two subjects that seem to be completely unrelated are actually linked together. So let me set the stage. So why do we even care about studying dark matter? Okay? So things you think we know by now, but we don't, is this big pie chart. So all the stuff that you have seen in that video, all the stars, all the galaxies, all the gas, everything you've seen there, you, me, this podium, everything, this room, makes up only 5% of the total matter in the universe. And so this 5% is the stuff we know, and even that one we know, there are a lot of unknowns even in that 5%. But at least the 5% we think we understand. There is another 20% or so where we have some idea, and I'll show you the research that led to the idea of what this dark matter could be. Yet we have not detected it, okay, directly here on Earth. So everything we've ever touched knowingly here on Earth goes into those 5%. Then we have 75%, which is the dark energy, and we have even less knowledge about that one. So today I'm mostly going to be talking about dark matter. And why is this so intriguing in a way? Well, just imagine, we've been studying matter, and I've stole this slide from PhD comics. We've been studying matter for a couple of 100 years, and we have a fine understanding of chemicals, etc. You've all been to school, you've all learned about chemistry, organic, inorganic, all these things. And so you live in this world where you think, oh, we know our materials, right? And then all of a sudden we discover that all that work we've been doing is only a tiny fraction of the total matter there is in the universe. So it's basically like you're studying the elephant, but then you realize you're really just studying the tail of it. So today I'm going to try to get to the body of the elephant. How do we do that? So the idea of studying that dark matter exists and the idea of measuring the properties of dark matter is actually not new at all. It dates back to 1933 with Fritz Zwicky pictured on this slide. So does anybody know why Zwicky is doing that? Anybody knows the story? So Zwicky was a professor at Caltech that nobody liked. Why did nobody like him? Well, he very often offended his colleagues. And in this particular moment, he's saying, well, all my colleagues are like spherical bastards. No matter how I look at them, they still look like bastards. So Zwicky was a genius, okay? I'm not defending him. I think he was a terrible man, but he was a genius. Scientifically, he was a genius. And in 1933, he looked at this particular galaxy cluster. This is a coma cluster, and has looked at the velocity of the galaxies moving within this cluster. So basically, you look at this image and you see all the orange galaxies that you see here are elliptical galaxies likely belonging to the cluster, and you can go out and you can measure the velocity of them. You take what we call a spectrum. If you don't know what a spectrum is, don't worry about it, but you can, trust me, you can go out and you can measure the velocity. How fast do these galaxies move in this cluster? And if they move very, very fast, yet they're still bound together, what would be the likely conclusion? Well, there is something holding them together. And that's something that's holding them together. It's a gravitational pull of the matter inside this cluster. So Zwicky did this experiment in order to measure the mass of the cluster. The faster these galaxies move, the more matter it needs to hold it together. The surprising result of this discovery was, though, that when he did that, he calculated the mass, and then he compared it to the mass of all these galaxies. People had good understanding of galaxies at that point, and they knew how massive they were approximately, and he realized that the discrepancy between the mass that he sees and the mass that he measures, the gravitational mass, is about factor of 400. Now, 400 is not a little factor. It's not like he got 20% more or something, right? He got a factor of 400 difference, and so he called the matter inside the invisible matter. The research went forgotten because nobody liked to play with Zwicky, and so nobody cited him, and things went things were not picked up. Until about 1970s, where Vera Rubin did a slightly different research in which she tried to measure the velocities of stars inside a single galaxy. Remember, Zwicky did galaxy clusters, thousands of galaxies. Vera Rubin does this on a single galaxy. So again, she went out and she measured how fast do stars rotate around the galaxy. And so if galaxies were only made of visible matter, what would happen, what Vera should be measuring, is this kind of velocity as a function of radius. So the further out you go, right, at a certain point inside, you're still picking up the mass. Here you see this galaxy, you're picking up more mass, so your velocity goes up. But then when you stop picking up the mass, your velocity should decline, just like it declines for the solar system. If you look at the planets further and further away, they get lower and lower velocities as they orbit around the sun. The same should happen with a galaxy. Yet what she measured was this one. Clearly different, completely different behavior. And so what Vera concludes from this is, in addition to this visible matter, there has to be a dark matter halo of about that size. Okay, so this was then another triumph for saying there is dark matter in the universe. But other than just sort of knowing that it's there, we had, until very recently, no idea what this dark matter actually could be. As I said, we haven't detected it here. None of the particles that we detected on Earth would work. And so the question is, what really is that dark matter? So we ventured on a research and started studying more galaxy clusters. So let's go back to Zwicky. As I said, he was a genius, right? So let's pick up on his research and try to answer the question of what dark matter really is. So this is a Hubble Space Telescope that I use for my research, and what you see here is an image of a galaxy cluster. This is Able 1689 with a phone number, and you see again a lot of these orange galaxies in galaxy clusters, and you can go out and measure the masses of those galaxies, the masses in stars and dust. And you realize, yes, there is a huge discrepancy between the mass you see and the mass you will measure later. I'll show you how. But so Zwicky called it invisible matter. And, you know, do you immediately jump to the conclusion it has to be some unknown form of matter? No, first, before you even jump to that conclusion, you want to exclude everything else possible to be this sort of invisible matter. And Zwicky did not know about one component of a very simple matter, hydrogen. Okay? What Zwicky couldn't see in those galaxy clusters is that they contain a lot of hot gas. Hot gas that's heated to 30 to 100 million degrees Celsius. Okay? A lot of Fahrenheit. So it's a really, really hot gas, and because it's so hot, it's invisible to optical telescopes. So why could Zwicky not see it? It emits in X-rays. What's the problem with X-rays? They don't go through the atmosphere. Very good. Yes, so unfortunate for astronomers, X-rays do not penetrate the atmosphere. Fortunate for humanity, because if they would, we would all be dead by now. But they don't, and so in order for us to see those X-rays, we need to again send telescopes up in space, and this is the Chandra Space Telescope, which we use to study those galaxy clusters. And, you know, the pictures aren't that beautiful, but they are telling you a lot about the makeup of galaxy clusters. And so it turns out that this gas is about 6 times more massive than all the stars than all the stars in galaxy clusters together. So everything that Zwicky could see, gas is 6 times more massive than that. Okay, so it's not a factor of 400, it's a factor of 6. Okay, turns out Zwicky's factor 400 was not measured correctly either. We'll get to this in a second. But so now you have another component, and now let's add gas plus galaxies and everything together. And when you do that, you still are missing a lot of material. About 80% of the matter is still missing. And so the question is, what is that matter that we cannot see? And right now, we are done with anything that we can see. So we scan all the possible frequencies, so it cannot be some normal matter in hiding, we realized. And so we would really like to get deeper into understanding what that matter is. To understand what dark matter is and how the clusters behave, we don't only use velocities like Zwicky said, but we use something much better, much cooler. We use a tool called gravitational lensing. And so how does gravitational lensing work? Well, if you have an empty universe with only Hubble and one galaxy, what happens is photons travel happily on a straight lines, and it would travel from this galaxy to Hubble on this straight path. Hubble would see this galaxy where it actually is. But now, by the magic of PowerPoint, I'm going to put a galaxy cluster in the middle. Okay? And so, according to general relativity, and don't worry if you don't know what general relativity is, but trust me, when you put a massive structure in the universe, the light does not travel straight. It's basically like all of a sudden, you are on a mountain and there is a big valley in front of you, right? So what would be the fastest way to come from one side of the ridge to the other side of the ridge? If you're a bird, you would just fly across, but you're not a bird. So you go down and up, but that's not the fastest. The fastest is around that thing, okay? So in the very same way, galaxy clusters create these potential wells, as we call them, and so the photons they still want to travel with the fastest way possible, and the fastest way possible is actually on this curved path. So this is faster for a photon than this one. Okay, but now Hubble doesn't see the galaxy where it originally was. Any guess where Hubble sees the galaxy? Further up along the straight line. Very good. So the galaxy is not there anymore, but it's there. Okay? Anybody sees another possible travel path that would be equally fast? Down below. So they'll see two galaxies. Only two? Can you think of more? Yeah. If it's everything is completely round and symmetrical, you can get a solution, of course, also outside of the panel and in on the other side. So you see two on the sideways, right? And in addition, you can see them all around. So you can get what we call Einstein rings. So full ring, instead of a single image of a galaxy, you get them stretched into a full ring. If things are not completely symmetric, other configurations can appear. And here are a couple of configurations that are near and dear to me. So I've shown you this galaxy cluster before. You see this really, really stretched arcs up here. So these are galaxies just like our Milky Way. But they don't look like our Milky Way because they've been stretched in these big circles. So here is one that's been almost completely imaged around. Of course, galaxies are not perfect circles, so things don't always go in complete circles. Very rarely do you see those. Or here is one that I studied. This was my very, very first research project. I call it the footprint of a Yeti. This is a galaxy. And this is 1, 2, 3, 4 images of the same background quasar in this case. So you get multiple images of the same source. So these things are very easy to find. Well, they're not that easy to find, but they're easy to recognize because those things do not usually happen in nature by themselves. So you're very sure that there is a lens in the middle or in the middle here. And the further apart they are stretched, the more massive the lens that's doing it. Okay, so that's how we can measure the mass of this object. If you want to try gravitational lensing at home, yes, but I'm not going to let you take the glass or the bottle. The only thing you're allowed to use is the stem of the glass. And so these are some images from my colleague Phil Marshall. You also need a light source, so you need your background galaxy. That would be the candle. And if you take the stem of the glass and you look at through the glass, at the candle, you will see 1, 2, 3, 4 images of the same source. You get to see the very similar configuration we saw on the previous slide. You can make a perfect Einstein rings as well. The reason for that being is that the refractive properties of that stem of the glass are very similar to how photons propagate in the universe in the presence of a massive object. And the thicker the glass, the more powerful the lens, the bigger this circle would be. And so that's the analogy of how we measure mass. But now let's go to one of the most exciting clusters in the universe, at least I think so, which is the bullet cluster, or it also has a really weird phone number that nobody ever remembers, but just think of it as a bullet cluster. So here is the bullet cluster as we imaged it with Hubble Space Telescope. So the cluster is a bit further away. It's not that easy to pick out, but again, you're looking for these orange galaxies, right? And you have two big galaxy clusters here. One is over here, and one is over there. And we measured the distance to them and realized that they're right next to each other, so they're interacting gravitationally. So now you take this cluster and you look at it. Of course, we want to see what a gas is doing. And so normally, if you have a galaxy cluster, and here's my Blackboard presentation. So if you have a galaxy cluster, you have galaxies, and you have a cloud of gas. In this case, we have two galaxy clusters. So these are galaxies, again. And you would expect, if they're happily living galaxy clusters, that this one would also have a cloud of gas. So you would see sort of gas on top of each of this, on top of each of the collections of galaxies. The surprising moment came when we took Chandra observations of that cluster. What we saw is not even nearly what we expected, which is to have one cloud of gas here and one cloud of gas here. Instead, we have these two clouds of gas squished in the middle. Okay, in addition, you can see this kind of shape. Okay, I didn't draw this sort of circular and spherically symmetrical just for fun. It's actually, this is how we see most of the galaxy clusters, right? You saw the coma, it just has this big blob, sort of spherical. You can see these are really, really squished, okay? And in addition, you have this bullet type shape, okay? Hence the name, the bullet cluster. So what happened is, these two galaxy clusters collided. Now remember from the movie, there is a lot of space in between galaxies, okay? The galaxies, they make tiny little spots in this cluster. Gas is sort of smoothly distributed. So when the two collide, these tiny little spots, they go right through. So the galaxies go right through. But the gas collides, okay? And it interacts, slows down, makes the pancake shape, okay? And so what happened after was this cluster went through the other cluster, and so now the little one is over here. Galaxies didn't do much, so I'm trying to draw them exactly the same, and failing, obviously, but you get the picture. The galaxies switch places, yes. I'm trying to, there is more than 5 in each of them, so one has 200 and the other one has 1,000. So if I draw all of them, we'll be here for a long time. But you're right, you're absolutely correct. The galaxies switch places. They went from here to here, right? So if you have 2 of them, they collided. So now they're on the opposite side. So now we have the little one here, and the gas of the little one slowed down from the little one, and it's creating this bullet type shape. And the gas from the big one is this pancake that you see there. And now I have the 2 galaxy contributions and the 2 pancakes in the middle. And if you want to know, so we are seeing this picture only at this point, right? We don't have a way to see it at this point. So if you now look at it, this is the trajectory. So the little guy sort of flew from the bottom, and the big guy came onto it. And so the little one was here, went through, and they swapped places. Exactly how you said it. So the gas slows down, and an analogy, not the greatest one, but if it's easier for you to picture, is, you know, when you're snow plowing and skiing, you sort of slow down, right? Or if you're surfing, you see this kind of shock in behind. So we can see this kind of bullet shape feature behind. But I don't like bullets, so that's why I prefer skiing and surfing over that. So this is now our bullet cluster. Now we want to know what the dark matter did. Okay, so this is our nature's own collider. We did not pay billions of dollars to build it, although we need telescopes that are almost as expensive to look at it. But we now have the nature's own collider, and so we can now study what the dark matter is doing. So we have collided 2 clusters, and if they have some dark matter, the way it's predicted, then we'll see what a collision did to it. How do we know where dark matter is? We are going to use gravitational lensing, and we'll study where the dark matter is. Now let's go back to this picture. So dark matter is sort of another cloud. It's very smoothly distributed of stuff in both of those clusters. So first of all, imagine there is no dark matter, and we do gravitational lensing. Where is most of the matter in this cluster going to be? The gas. Remember, I was telling you gas is 6 times more massive than galaxies. So if we do gravitational lensing and we try to figure out, remember, gravitational lensing doesn't care what kind of matter it's measuring. It's just measuring the total mass distribution. You would get the peaks of the mass distribution sort of on top of each of those little clouds. If there is dark matter, though, and dark matter acts like gas, then you would still see it on top of the clouds, because it would do the same thing. It would pancake. It would get slower. But if dark matter behaves like galaxies, it does not interact. If it's non-interactive, if two dark matter particles don't do anything to each other, it's like Harry Potter, they just go through the walls, right? Then you will see distribution of mass on the galaxies, because it will just do the exact same thing as the galaxies do, not interact. And the big result, you see now in pink is the gas from before, and you can see now in blue is the result from measuring the total matter in this galaxy cluster, and it perfectly lines up on galaxies. So we know that that dark matter does not interact a lot. In addition, we know it's there, right? Because if there was no dark matter, remember the peaks would end up on the gas rather than on dark matter. And so this was one of the big successes of telling us that dark matter actually exists, and you cannot just fudge the gravity a little bit to make it happen. You really need an extra component. So a student of ours, who is now a professor, has created this movie. So what this movie is showing, let me just describe it in a second. We're going to collide two clusters of galaxies in a computer simulation. Red is gas and blue is dark matter. And he managed to adjust the parameters of dark matter such that the end result matches the observation. So you see two clouds of dark matter going through. The gas is interacting, so it sort of splashes together, makes these pancakes, makes the bullet, whereas the dark matter itself does not do anything and just goes straight through. So this is a little bit of a turn around to see this particular configuration, and in a second we'll compare this to our observations, and you will see that it matches pretty well the actual observations of the bullet cluster. So this is just for aficionados. This is going to go very technical. If you don't understand anything, just snooze for this one slide, but it will get really exciting just after. So basically, as I said, the two galaxy clusters collided, and because they're not interacting, we can say that the interaction cross-section of dark matter is very small. And so we can put some limits on it, and the limits that we are currently getting from simulations is about 0.7 centimeters square per grams. Now, particle physicists don't understand these units very well. This is 1.3 barns per GeV. If you have ever taken any particle physics course, you might say, oh, this is a big cross-section. So yes, the limits aren't all that small yet, but this is the first time that we are actually measuring the limits of self-interaction cross-section.
Why did it come centimeters squared per gram, not cube?
Because what matters is the frontal cross-section. So you're basically, it doesn't matter when you collide two clumps of particles, it doesn't matter how many you have in front or in the back. All it matters is how many you have in each individual sheet. So that's why it comes to centimeters square. Per gram is because we don't know what the mass of the particle is. Okay, so all we can measure is, imagine having a smaller particle, then you would have a larger number of them for the same density, or you can have a bigger particle and you would have fewer of them, and they would sort of make the same effect. That's why we cannot distinguish between the two. So, but this was the first result, and the conclusion was the dark matter is mostly collisionless. Whenever you do scientific research, if you have one case, everybody says, but what if it's a pink elephant, right? So just one case is not going to cut it, so we are trying to find more bullet-like clusters. You want to confirm this result, right? In biology or medicine, you rerun your experiment. In astronomy, you just go find another system like that. So how do we find more bullet-like clusters? This sign suggests, anybody recognizes where this is from? Yes. Very good. It is from Squaw Valley, and it's just pointing you up straight into the sky. So that's where you look for. And so we went and we looked, and basically what you want are you look for two galaxy clusters, and you try to look at them with Chandra and see what the gas is doing with those two clusters. Because if you catch them before the merging happened, the gas is going to be right on top of the two components. Whereas if you happen to see them afterwards, the gas would have interacted and stay in the middle. And here is what I call baby bullet cluster. It's neither baby nor a bullet. It's older than a bullet cluster, so it shouldn't really be called baby. But it's a max JO 25 minus 1222. And again, you see the two galaxy contributions, the gas smack in the middle, and the dark matter following the exact same picture as the bullet cluster. And this is not all of them. Here is even more. We have Able 520, we have baby bullet, we have musket ball. We tend to give them cutesy names because there are so few still. But now we are getting in the point where we are sort of getting into the numbers of 20 and above. I think we'll stop naming them, I hope. But you can see all these numbers down here. These are the cross sections that we measure. All of these clusters are telling us exactly the same thing. Dark matter is collisionless. So will we ever do better? Right now, we have a large merging cluster collaboration, or MC squared, at UC Davis. And this collaboration is trying to find more of such clusters. So in the future, there will be many more. But right now, we already know that dark matter is collisionless, and mostly collisionless to the accuracy we can measure, and that dark matter really exists, and we have measured some properties. All right, I'm going to now switch to something completely different. So this is not dark stuff anymore. This is my baby galaxies, and this time it's really baby galaxies. So we are trying to measure galaxies at a very early universe. So some of you might know universe is 13.7 billion years old. Started with a Big Bang, and about 400 million years later, first galaxies form. And we want to see those very first galaxies, because these are the progenitors of our own galaxy. How do we study those very first galaxies? First of all, let me tell you why do we want to study them. Okay, just jumping ahead a little bit. So as I said, universe is 13.7 billion years old. This is when it started, Big Bang. We have here cosmic microwave background. I don't really have time to go into this, but about 400 million years later, we get the first stars and the first galaxies to form. Before that, the universe was a very boring place. It was full of just neutral hydrogen, no light, optical light could go through, and so it was just dark and boring. So that's why we call it cosmic dark ages at that point. When the first stars and galaxies came about, though, they basically wiped out the fog. Okay, so imagine like the sunrise comes and all of a sudden all the fog is gone and all of a sudden you can see. And it's the very same thing happened with the universe. We wiped out the cosmic fog, we started a cosmic dawn, and the first stars and first galaxies were the ones who were doing this. And so this era we call reionization. So we are trying to find those very first galaxies and try to figure out how to explain this process. How do we study those very first galaxies? It's quite tricky, because you can imagine if you put something very, very far away, it's going to get very, very, very dim. Okay? The further away things are, the dimmer they are. In addition, what happens in the universe is that the light gets redshifted, meaning anything that's further away looks redder. It's a similar effect to the pitch of the train changing when it's moving away from us. Okay? And so in the very same way, we get those galaxies to be redder and redder. Because they're redder and redder, our optical telescopes struggle with them. And so what you need is infrared telescope. But Hubble in 2012, before 2012, they installed the very new infrared camera called Wide Field Camera 3. They're not very, they should give them cutesy names. But that camera is an infrared camera that allows us to study those first galaxies. As I said, those first galaxies are very, very red. And so what happens is, again, this is getting a little bit technical, but I'll explain it in a second. So here we have a spectrum of the galaxy. Once you move it at a high redshift, as we call it, or very, very far away, what happens is it gets very red. So if you then look in different filters, this is just like your photography. This is your bluest filter, less blue, red, infrared, infrared. You don't see it in your blue filters because the galaxy is red, but you see it in your reddest filter. Okay, so you can see this galaxy, you can see it in those J and H color, as we call them. So these are your reddest filters. So you look for something that's very red, and the reason for this is you want to answer question now about the epoch of reionization. First, who did it? I told you it's first stars and galaxies, but we aren't really sure. How exactly did it happen, and when did it happen? So when did this cosmic fog clear? Okay, we want to study the first galaxies. Those are far, far away. For that reason, we need assistance. Okay, how do we get assistance? You might have guessed. Adrian mentioned it quickly. It's gravitational lensing again. So this is a slightly different slide, but it's the same principle. You have a background source, the light gets bent, and because it gets bent, galaxies appear in different spots, but not just appear in different spots, they get enlarged. Okay, it's just like your magnifying glass. You take your magnifying glass to make things bigger so you can see it, okay? And so you get it magnified, and because of that, it also becomes brighter. So if you look at galaxies behind those big galaxy clusters, you get to see them brighter for no extra cost. So we went out, and we are now doing a search for those very first galaxies. And first of all, you want to know that they're indeed at those highest distances. So we want to measure distances to those galaxies. And the reason I'm a little bit sleepy today and not very eloquent is because I just returned back from Hawaii. We were observing galaxies, those very first galaxies, with an instrument, with Keck telescope, with an instrument, brand new instrument called MOSFIRE. So this is the observing team. This is me and my student in front of this thing. Is actually 10 meters big, so it's a very large telescope. And here I'm showing you some very, very preliminary results. So this is what I call the Three Musketeers survey. It's Keck, HST, and Spitzer study of galaxies at the highest redshift. And I know these don't look particularly exciting. This is not like Hubble images. Like all we see, right? Remember, this is your two blue filters. These are your red filters. You see these smudges. And in addition, we took a spectrum of this thing, and we can see the galaxy right here, which tells us that it's at the redshift 7.42. It's the second highest redshift ever discovered spectroscopically. And it's a relatively faint galaxy. So we are not looking at the brightest of them. We are looking at normal galaxies at those epoch. So that's some very exciting result. Another exciting results are right now coming from a different type of survey. So once we find those galaxies, we know where they are, and we know how far away they are. What then? What you really need is you need to study their stars. You need to figure out how much power they can emit in order to clear that cosmic fog, right? If you have very, very foggy day, the sun might not burn through the fog throughout the entire day. You know this. You've been to San Francisco in the midst of the summer and was wearing a thick sweater, right? So you need a powerful enough source to burn off the fog. So how do you know if it's powerful enough? Well, you study their stars. So for that reason, we started the SURF survey, or Spitzer Ultra Faint Survey Program, as it stands for. I hope I'm not getting into trouble for this logo. But it's a large Spitzer program. Spitzer is another space telescope that observes in the infrared. And we are studying galaxies for 550 hours. We are controlling Spitzer and studying whether those galaxies actually have old stars. another technical slide. How do you know if the stars are old versus young? So you look at the colors at the galaxy with Spitzer, and it turns out, okay, if you are too tired to understand that, don't worry about it, but you can look at a spectrum and you can see these jumps right in the Spitzer channels, okay? So this is flux as a function of wavelength, and so this is your VIPC3. These are the ones I showed before. This is the near infrared. This is the less near infrared, I should call it. So it's a channel 2 and channel 1 and channel 2 of Spitzer, and you can see different galaxies plotted here. And this one has the oldest stars, and this one has the youngest stars. And you can see how very different they are. They don't have this characteristic bump at 4,000 angstrom rest frame wavelength. So this characteristic bump tells you that there are old stars in that very galaxy. So here is the bullet cluster. You might not have guessed that, but this is the Spitzer image, and this is the main cluster from before. This is the subcluster. And now all the galaxies at lower redshifts, they look similar, but at the highest, the faraway galaxies are here, tiny little specks, and I had to put circles around them so you can even know where they are. You cannot really see them because they're so faint, but here is one of them. And you can see again, these are your blue filters, your HST filters, and these are your Spitzer filters. Of course, Spitzer has a poorer resolution, so it looks even more ratty than before. But what you can see here is a spectrum, and you can see this bump, okay? And this tells you this galaxy has old stars. And this is the exciting part of we just published this paper. Actually, it's to be sent off today or tomorrow probably. 600 million years old stars in a universe that at this point is only 800 million years old. So previously we thought stars should have started forming 400 million years after the Big Bang. Looks like we'll have to push this limit earlier on. So stars seem to start forming much earlier than we expected. And here is an even further one. This is behind another galaxy cluster. Again, you see this bump, meaning old stars. 400 million years old stars in a universe that is 500 million years old at that point, because this one is further away, so we see the universe as it was even younger. And so it's exciting because now we know stars starting forming even earlier than we thought, and we can now finally study the output of all these galaxies and figure out whether they can make responsible for reionization. So I'm going to summarize here. As I said, first galaxies have started forming stars much earlier than first thought. Dark matter exists. I hope I convince you of that. I'm happy to hear alternative explanations too, of course. But the question is, why is dark matter so difficult to detect? Why haven't we detected it here on Earth? Well, first of all, I didn't mention to you, but there is 5 times more dark matter than there is any other matter that we know of right here. And so there is a lot of dark matter. It's much more abundant, so it's not a problem of abundance. But here on Earth, the problem is dark matter is spread out much more. Okay? Here on Earth, there is a tiny density of dark matter. There is dark matter right here. I firmly believe in that. In fact, depending on the mass of the particle, probably in this room we have 1 to 2 dark matter particles. Yoo-hoo! Let's go find them. How many other particles do we have? Who knows Avogadro number? 10 to the 23rd, right? In every mole of gas, which is, about that much. Roughly. So, in every single piece you pick, it's, 10 to the 23 particles. There are 2 dark matter particles. Don't take me by this word, It could be 100, it could be less, but, of the order of. And so, in addition, as I told you, it doesn't interact. Dark matter just goes through. And so it's very, very difficult to detect it. And so the experiments are there trying to search for dark matter. And so far, we have only had the exclusions. But hopefully the LHC will tell us exactly what dark matter is. But until then, astronomers have figured out quite something about dark matter. And I'll finish my talk with a slide from Sean Carroll, which says, dark matter, most of the universe still can't be bothered to interact with you. Thank you very much.
Marusa, if I can kick off with the questions. So what is thought to be the origin of the gas within the galaxies, and how fast would it take interacting galaxies to build up, if they can build up another galaxy gaseous halo after they've interacted and they've had these stripped off each other?
So what it will happen here, it's not completely stripped off, right? What I didn't mention, I mean, you see these tiny patches of it, but you should really think about this as each galaxy cluster being, you know, from here to here, right? So these are big structures, and this is just their centers. So eventually they will go through, and the gas, because of the gravitational pull of dark matter, will reconvene. And so that's why most of the times in the universe, we see them like this. We see the gas being associated with galaxies and the dark matter halo. So just imagine, it's the same thing. You know, if you throw up a stone, it's going to come down back on Earth. It's gravity, right? And so in the very same way, the gas is going to be pulled back into the potential well. What's the first origin of these things is basically you start creating these structures by having little seed overdensities of both dark matter and baryons. And so you have these two little overdensities, they meet, they merge together, they combine, you get a bigger structure. And these structures have gravity acting on them. Remember, dark matter does not interact with each other, but it does interact through gravity. Okay, this is something I forgot to really stress. But it does have the gravitational pull, and so it pulls the gas from the surrounding in, and so that's the origin of the gas. It gets then heated because the well is so deep.
At the beginning, you mentioned that you talk about the gas, but at the same time, you said it's 100 million degrees Kelvin.
Yeah.
Under these conditions, gas cannot exist. You would have completely plasma. And the question is,
plasma.
Would you even consider that the nuclei would separate into neutrons and protons, and that maybe the dark matter that you don't see would be just clouds of neutrons?
Dark matter cannot be clouds of neutrons. We realize that because you cannot make enough neutrons to start with. Okay, and it behaves differently.
Also, bare neutrons are unstable. They decay in 15 minutes.
Yeah.
Okay. That's bad news.
Yes. So it cannot be neutrons, right? And this is plasma. I speak vaguely, you know, gas.
Yeah,
people can.
You always hear gas.
Yes, but no, it is actually plasma. But that doesn't change any of the conclusions, obviously, right? Plasma still, there is ram pressure stripping inside the plasma, and so the whole process goes in the exact same way.
Hi, I'm Humphreys and Associates. I'm not a physicist or an astronomer, I'm just an engineer. So my question is, from my understanding, it's cold, warm, and there's hot dark matter. I didn't hear any description of that. And there's a new instrument being built down in Chile at some point. It's going to be installed.
Yeah.
About infrared. Do you know Charles? From Smithsonian. Okay. So answer those other questions about cold, dark, and warm.
So the dark matter, yes, it could be either cold, warm, or hot. So hot dark matter would be neutrinos. So for a while, there was an idea that we can make these things out of neutrinos. However, the problem with hot dark matter is, as the name suggests, it moves very fast. So when you're forming the structures in the universe, this fast movement prevents the smallest structures to form. And so we would see a very different universe today than we do see. So the structures, the galaxy clusters, the way they would form, they would look very different. So it cannot be hot dark matter. It can be cold dark matter. It's very likely cold dark matter. It can still be somewhat lukewarm, okay? Sort of mixed between warm and cold. But it's definitely not hot dark matter. So all the observations we have are perfectly happy with cold dark matter scenario. And that's the simplest scenario we can think of.
Okay.
Yeah, if you have a question, sit down and put up your hand and I'll get it.
So speaking of neutrinos, you gave us an idea of the relative abundance of dark matter in the room versus normal matter. Where do neutrinos fit into that spectrum? How many neutrinos are in the room, roughly? Anyone?
There is a lot of neutrinos in a room.
So neutrinos are way more common than cold dark matter.
Yes, neutrinos are way more common. They're less massive, so by mass, you need to think about that way. But in terms of numbers, because their mass is so small, there is a lot of neutrinos. But the problem with making these galaxy clusters out of neutrinos is neutrinos are fermions. They don't like each other. Okay, so sticking them together, it's really, really difficult. And so making these high densities of dark matter that we see in these galaxy clusters, like right here on Earth, the density is not that high, but in there, the density is really high, relatively speaking. And so it's very hard, it's impossible to make galaxy clusters out of neutrinos.
And then that leads into the other aspect. How dense does dark matter get in some of these scenarios compared to the density we're used to with ordinary matter?
So the ordinary matter is much denser, okay? You cannot do this with dark matter, right? And anywhere, because so everything here is governed by the electromagnetic force, right? And so that's why you can make material really dense. Dark matter interacts only via gravity, maybe via weak force. And so that's why you cannot make densities are not high, okay? So they're much smaller densities. And that's what I said, few particles. And the masses that I'm quoting are sort of proton masses. So think about few protons per room right here.
Very helpful. And neutrinos are so much lighter than electrons. That helps put everything together. Thank you.
You're welcome.
When I listen to this dark matter stuff, and seems like we cannot touch it, we cannot taste it, we cannot see it, and we say it is there. And the main factor is the Einstein's theory of relativity.
Yeah.
And why we don't think that just theory of relativity is just wrong? We tested it only on Earth, or
That's an
just around.
excellent question.
I think it's much more logical to think that we don't have just theory which describes this whole.
And that's what people have started with the very beginning. They said, okay, gravity is wrong. And that's how modified Newtonian dynamics came about. And so you can do this remember Zwick's experiment, right? He just figures out there is a factor of, in our case, it's actually a factor of, once you add all the gas, maybe less than 10 difference. So you just modify your gravitational constant and you solve the problem. But you modify it in clusters and then the galaxies don't work. In the galaxies, you have to modify it by a different number. So this is one problem, but then, and you can still live with that, right? The bigger problem that I have here is, in this case, of the bullet cluster. So that's why the bullet cluster result was quite important, because now not only, remember, if it's just baryonic matter, the total mass distribution should peak here. No matter what gravitational constant is, it should be here. Right now, if you want to explain bullet cluster with a modified gravity theories, you have to also change the direction. So it's like, I'm standing here on Earth, instead of being pulled here, I'm being pulled over to that direction.
But you still stick to the original theory. Why not assume that we observed it only on Earth and in our solar system? How do we know that it works very well in so vast,
Yes, no, it's a
space? So it's like, it reminds me the situation on the turn of the century when they were looking for a sphere, And it was had exactly the same qualities. You could not touch it, you could not feel it, and finally Einstein showed that there was no interference.
Yeah.
So
It's,
very much.
it is a possibility. Is right now that would be even harder to do than predicting a new particle. So the simplest solution is predicting a new particle, because as I said, a theory of gravity which pulls away from the gravitating object is a really hard thing to do, and nobody.
You use the old mathematics.
We have another
Yeah.
question.
Okay, I'm sorry.
You've presented some very beautiful data, and I would just say that one must be a little careful about the conclusions that you reach. What I would say in very simple language has been shown, particularly in the bullet cluster, is that there is a gravitational end in the halos which are doing the lensing, that there is something which is having a gravitational effect, which is on a geometric scale much less dense than the ordinary matter that we're familiar with, point one. Point two, that in a collision process, this something which has those properties doesn't seem to interact with itself at all. It just passes right through. And of course, the concept of dark matter would fit those characteristics. But there's something else which is even simpler, and this has now been put out in not quite in the literature because not yet published, but it's part of something which is also a modification of the fundamental theory. That is to say, if we go back to Hermann Weyl, who proposed something which is a theory of gravity in 1918, and we really follow the implications of that, it's now been pretty clearly established that you can account for the Hubble expansion, and you can account for the excessive velocities, which are the main source of dark energy, and you can account for halos, the dark halos, without dark matter. I'd like to talk to you about this afterwards. But the crucial thing in the halo, which has those properties which I mentioned, which characterize the data that you're talking about, is a simple vacuum. Absolute lack of matter. What? How do you get a gravitational effect? If you are familiar at all with impurity scattering in solids, you realize that if you have a medium which has a density in it, and you go to gravity, and you have a geodesic coming from that medium that enters an empty hole, it will be deflected.
Yeah.
That's known as gravity. But then it's the nothing that does the deflecting, and nothing does not interact with nothing. Therefore, you have that fact that you attribute to
Yeah,
dark
we should
matter.
talk about this. But there is a lot of research going on right now in modifying gravity to explain dark energy, for example, and that's been very fruitful. The modifications you do actually do not affect these scales, though, for that kind of, because you modify the universe as a whole rather than individual. Yeah.
Okay. Question, are we sure that this dark matter is within our three-dimensional universe? Could be slightly displaced by a small amount into a fifth dimension or something, so you're only feeling its gravity and can't
Well, but then you
otherwise.
have to move the background sources too. So if you believe
Yeah.
that galaxies are in our dimension, then dark
Yeah.
matter needs to be in our
And
dimension too.
I take it the old controversy of machos versus wimps
Yeah.
has been settled in favor of wimps?
Yes, absolutely. Machos cannot explain they can still be there, but they can only be a small amount of total matter in our galaxy. Unfortunately, we didn't see many of them.
Hi, I have a big dumb question.
There are no dumb questions.
There are, but this is one of them.
Those come from politicians.
So in other talks, I've heard that basically elliptical galaxies are the result of colliding spiral galaxies, as far
Yes.
as we can tell. So that the presumption that I have then is that the earliest galaxies would be spiral galaxies. And so my big dumb question is, I know that matter and dark matter cause clumps of mass to connect and compress and light up and all of that. Why was it spinning?
Why was it spinning in the first place? Because things don't just didn't just statically evolve, right? If you say you have two objects, they are at rest, and now you let them go, gravity takes over, right? And they do this, right?
Could inflation have had something to do with getting that started?
Inflation got to do with starting the first seeds and how they formed, and then gravity takes over and makes the angular momentum for those things. But that's a question that we do in our research all the time, and have entire conferences that are, so it's by no means dumb question, okay?
Yeah, going back to the bullet cluster, you talk about how the gas cloud will eventually kind of merge back into the center of the cluster. Is there any sense that that gas cloud would sort of oscillate and kind of bounce to the other side of the galaxy, kind of an oscillation?
Yeah, it's sort of, it's just simple gravity falling in, so you get a little bit of a sling, and then it eventually slows down.
So have you looked for or found any examples of where the gas cloud, I guess,
it's ahead?
Is ahead?
No, you can see those things. You can see the slushing of the gas in galaxy clusters, for sure.
Okay, thanks.
Last question.
Excellent. So I have the honor of the last question. So when you were explaining that the dark matter forms a cloud or rings around, I mean, just with my very basic understanding of gravity, it seems like it's not actually acting with what we consider to be typical gravity, because otherwise, if it was interacting from a gravitational standpoint, it would actually start pulling inside of itself, would it not? Would you not get a pinpoint concentration? So why are we seeing a halo effect?
So this goes back to that question, because there is also angular momentum. So it's like, why didn't all the planets end up in a sun when the solar system formed, right? I mean, there is some angular momentum which prevents that. And so when the things collapse, they cannot collapse. Also when the stars collapse, they only collapse to a certain point, and then the radiation pressure kicks in. And so for dark matter, that of course doesn't apply, but what applies for dark matter is it's simple angular momentum. So if something is spinning, you cannot get it to form into a single pinpoint.
Just as a quick follow-up, but then wouldn't you expect there to be at least some sort of even, quote-unquote, even distribution, though, of dark matter?
And there is.
Oh, it is, okay.
So if you look at the images, if you look at this kind of images, you see that's why I drew it as a sort of a smooth distribution. It still clumps a little bit more around galaxies, so you get little dots around galaxies because they have their own potentials, so it falls in. But most of it is smoothly distributed. It's concentrated towards the center, but so it's still basically, think about the sphere. And if all the particles would have direction straight to the center, they would indeed collapse in a pinpoint. But because they all have different velocities, randomly distributed, it's just like gas cloud collapse. You end up with something that's more dense at the center and then less dense outside.
Marusa, your topic lets me do this. Inevitably, we have a mug here for your own dark matter to collect within.
Thank you. And I love
partake it in Hawaii as well.
Yes.
Please join me thank you for Marusa for a great talk. If you have any other questions, I know there will be some other questions up there, so please come.